right, we're going to look at some practice problems now. We've talked about a number of math concepts. Let's look at some concrete examples. Okay, so for the first one, we're going to look at an inner product example. Here, our field is the reals. Our vector space is Rn. We want to show that this defines an inner product. That is, this summation. That is x, the kth element of x times the kth element of y, the sum of those from k equals 1 to n. Okay, so this is very similar to what you've seen before as a dot product. All right, so we're going to go through and show that. So if I now do y first and then x, this is that. Okay, but notice that individually these elements commute, so I can write them in the opposite order, and this is in fact the definition of x and y. This quantity, since we're working with reals, so if we go back over here, field is the reals, vector space is Rn, that is the real n-dimensional vectors, then this quantity is a real quantity, and so it is equal to its conjugate, and so we have the inner product of x and y is equal to the inner product of yx conjugate. So we have that. Next we have x plus y inner product with z, and we can write it out this way. Okay, so x plus y, the kth element, times z. I can distribute the z through this sum, and when I do now, I get this expression. So this sum is actually the definition of the inner product of x and z. This sum is, I can break this up into two sums. This sum is the inner product of y and z, and so we have the sum of x plus y inner product with z is equal to the inner product of x with z, inner product of y with z. Okay, so that's the second property. The third property, I take x and a scalar times y, and so when I express it this way, the scalar actually I can bring out front, and actually I can bring it all the way out front and get this expression. So this is alpha times the inner product of x and y. Finally, when I take the inner product of x with itself, I get the sum of the squares of the elements of x. Okay, clearly this is greater than or equal to 0 because each of these terms is non-negative, and so a sum of non-negative things cannot be negative. So it must be greater than or equal to 0. But when can this equal 0? This can only be equal to 0 when all the elements are x. If any one of these guys is not 0, then this quantity is going to be greater than 0, because x squared is, and x squared is, if x is not 0, x squared is greater than 0. So the only way we can have equality is if and only if x is equal to 0. If x is equal to 0, the sum of the squares is 0. If this sum of the squares is equal to 0, that means every element must also be 0. So we have that the definition for the inner product that we have satisfies those four defining properties for an inner product. So therefore, it is indeed an inner product. So until we actually prove it, we can think of it as an inner product, but until we actually apply it, we won't necessarily have that. So it turns out this definition we can actually go through and show that if I define x this way as a row times a column, then that's actually what we're actually getting here. We have this matrix multiplication. So I can think of this now as x transposed. So transpose is turning rows into columns, columns into rows. So x transpose, which is now a row, times y, which is a column. X transpose y, then, is an inner product, and we've just shown that it is an inner product for reals. For reals, yeah. Second inner product example. Now I want to take f as the reals. The vector space is a space of continuous functions defined on the interval between 0 and 1. So we want to show that this defines an inner product, the integral of x of t, y of t, dt. X of tau, y of tau, d tau, over that interval. Okay, so we go through and we look. Inner product of y comma x is the integral from of y x, and again, x and y commute, and so I can write it this way. But again, this is the definition for the inner product of x and y. So I can take the inner product either way. Again, because we're talking about real functions, this is a real quantity, and so this is also a real quantity. So but it's also its own conjugate. Again, if I take the sum, that's x of y plus x of tau plus y of tau. That sum times z. I can distribute the z. So I have x of tau, z of tau, plus y of tau, z of tau. I can break this integral up into two integrals. The first one is going to give me the inner product of x with z. The second one is going to also give me the inner product of y with z. So it satisfies the second property. The third property, again, when I take the inner product, I can take the alpha out front, and in fact I can take it again all the way out front. So alpha times the inner product of x and y is what we have. Finally, the inner product of x with itself, I have the integral of x squared d tau. So this quantity is going to be positive unless x is, that's a funny looking equal sign. That funny looking equal sign is basically is equivalent to. And so a number can be equal to 0. A function can't be equal to 0 unless we're talking about 0 at every point along that function. Okay, so that's what this is saying. X is equivalent to 0. That is, every element is 0. If any element is not 0, then when I integrate, if I have anything that's not 0, I'm going to integrate something that's positive, and this is going to give me a positive value, even if it's just tiny. Even if it's just tiny. Anything that's not 0, it will integrate and give something positive, and therefore this quantity will be positive unless it's equal, identically equal. That's what this is saying, identically equal to 0. Okay, inner product example number 2. Moving on to example number 3. I talked about a vector space being a space of polynomials, n-dimensional. So here's an n-dimensional polynomial in T. So P of T. T is the polynomial that we're working with. Okay, so I have the coefficients a0 to an. I can go through and take these coefficients and I can rewrite this sum as this vector product. 1t all the way to t to the power n, and then the coefficients. So I can actually write it this way. I'm going to give this guy the symbol that. Okay, so obviously it's a function of t. It's a vector that involves t and its powers up to the nth power. Transpose. So it's rho, and that's why it's transpose, times a. A is this, the column of all the coefficients of a. So P of t is defined, we can actually write it out this way. And suppose we now have another polynomial, Q of t, that has another set of coefficients that are b. Okay, so any nth order polynomial can be written in this form. Okay, so I'm going to define some w of t that's greater than or equal to 0 on t in the interval between minus m and m. And I'm going to define the matrix W, well, a lot of definitions going on here, defined between minus m and m as this quantity, w of t, the integral of wt times that psi, that is actually the Greek letter psi. Some people think it looks like a pitchfork, so they just call it pitchfork. Okay, so pitchfork of t transposed. So if you look at this, this is a row, this is a column, this is a scalar. When I multiply all this out, this becomes an n by n matrix. I'm sorry, n plus 1 by n plus 1 dimensional matrix. Okay, so I'm going to integrate that n plus 1 by n plus 1 dimensional matrix between minus m and m. So the integral of a matrix is basically I integrate each element individually. So I have all these integrals I have to compute. But they're simple because remember t is just t in its power. So integrating t in its powers is fairly straightforward, right? Integral of t is t squared over 2. Integral of t squared is t cubed over 3, and so forth. So it's actually a fairly straightforward integral. The only question is how is w affecting all that? So W can make things really complicated. So I can think initially of W, this little w, as being just the value 1, which satisfies this condition, in which case I have that. So W is referred to as a weighting function. So when I compute the integral from minus m to m, this will just be a numeric matrix. Okay, it will just be a numeric matrix. So even though it looks really complicated right now, this will be an n by n plus 1 by n plus 1 matrix. Okay, so we can now go through and show that if we define this as our inner product of p and q, a polynomial p with a polynomial q, then we can actually go through and show that this integral is actually equal to this product, A transpose Wn times B. Okay, so the reason this works is because Q is equal to C transpose times B. P is equal to C transpose times A. But again, I have a row times a column, I get a scalar. That scalar is its own transpose, and so you can actually go through and show that all of this comes out to be this. That is, I can take the A transpose out of the integral, the B out of the integral, and what's left inside the integral is all of this stuff. Okay? So anyway, this defines an inner product on that space of polynomials. So that space of polynomials obviously is more complicated than an n-dimensional vector, but we can still define an inner product on it. All right, inner product example 3. So you can go through and show that this satisfies all those 4 properties for an inner product. I'm not going to do that, but you can go through and show that that's the case. So one more thing. This, remember when we saw the first example, we had X transpose times Y was our inner product. Our inner product actually came out to be that. So notice this is not too different. A transpose times B with something in the middle. Okay? And that something in the middle is positive. So it turns out it has to be positive or all of this won't work. All right. Orthogonal complements. Let's talk about orthogonal complements. So let M be the space of vectors that look like this, where alpha is a complex value. Okay, so this is the set of all vectors that look like this. I have a complex value and 0. Let N be the space of all vectors like this, where I have 0 and a complex value. Okay, so the problem is show that M and N are orthogonal complements. So let Z be some value A and B. Clearly, you can write that this way, right? I can write that as a vector A and 0 plus a vector 0 and B. This vector I call X. This vector I call Y. Clearly, X is in the set M. Y is in the set N. And so we have shown that any vector in two-dimensional space, two-dimensional complex space, can be written as a sum of a vector in M, sum of a vector in Y and N. So therefore, M direct sum N is all of C2, two-dimensional complex space. Okay? So we can also show that the intersection of these two vectors is when beta is 0 and alpha is 0. Okay, so this vector is the intersection. That's the only way you can get an intersection, is if both those elements are 0. Finally, if X is in N, Y is in N, their inner product, when you multiply this times this, you get 0. So notice this is any vector in M, because alpha is, I'm just letting it be whatever. And here I'm letting beta be whatever. And so I'm taking the inner product and I'm getting 0. That shows that M is the orthogonal complement of M. M is the orthogonal complement of N. Okay, so we've actually shown a number of things by this particular example, what orthogonal complements look like, and so forth. Okay, so it's just seeing a simple example can make a huge difference in our understanding of these kinds of things. Finally, the range. So let the input space be R3. I'm sorry, not finally, but next we look at the range. The input space is R3, output space is R2, and our linear transformation is a matrix. So here's our matrix A. It's 2 by 3. So when I take A times X, I get this. Notice that X could be X1, anything X1, X2, X3. The result is X1 and X2. And so if we think about range for this operator, the range is all of R2, since any element in R2 can be represented by an appropriate choice of X. Okay, so this is an element in R2, and so if I start off with an element like this in R3 and multiply by this, I will get that. Okay, so the range is all of R2. So I have a three-dimensional space that maps into a two-dimensional space. Okay, so this is an example of the range. All right, next we have a 3 by 3 example. That is, the input space is R3, output space is R3. Here is our operator, which is a matrix. This matrix is a matrix of all ones. When we multiply by X, we basically get the sum of the elements of X. All the elements are that. I can factor this sum out and get this times all ones. Okay, so in this case, the range of the operator is the range of A. I can think of it in terms of the range of a matrix. And that's the span of all elements of all multiples of this vector. Okay, and clearly that is contained in R3, but it's definitely less than all of R3. So in general, again, for a matrix, a basis for the range can be found from the independent columns of the matrix. In our case, our matrix had all ones. Therefore, the independent, it only had one independent column. Okay, so this is a basis for that space. We'll talk more about bases in our lecture next time. Okay, so we have this matrix now. What is the range of this matrix? Well, if I look at this matrix, I can see anytime I have zeros in a matrix, that actually simplifies some of the calculation. So I can see that there's no way that this column can be a multiple of this column. There's nothing I can multiply this column by to get a 1 here. Okay, similarly with that. So I can see that these two columns are clearly independent, but what about this column? Okay, so that's a question. So I have at least two independent columns. If I actually go through and compute the null space of this matrix, and we'll talk about null space next time, I get this vector is in the null space. So what that means is that the columns are dependent. For an n by n matrix, in this case 3 by 3, to have a non-zero element in the null space means the columns are dependent. What this is saying is, if I take -1 times this column, plus 1 times this column, plus 1 times this column, I will get 0. Or another way of saying it is, if I take this column, if I add these two columns together and then subtract this column, I will get 0. So these two columns are independent, and so the range then is the span of those two columns. Notice that this column and this column is also independent. I could use this column and that column instead. Okay, but I only need two columns to define the range. Okay, here is a matrix, and I have a couple vectors. So, question, or rather, here's a statement. V is in the range of A, and V2 is not in the range of A. Why? So, to show that V1 is in the range of A, I would need to show that there is some vector x that when I multiply by A, I get this vector. And to show that V2 is not in the range of A, I would have to take the A multiplied by some vector x and show that there's no value of x that I can multiply A that will give me that vector. Okay, so that's what you would need to show. So I'm not going to do that for you. I'll let you think about that. So, practice problems. Thanks for watching.